Equilibrium notes example 3. So here we have a reaction being described as nitrogen gas plus 3 hydrogen gas going to 2 NH3 gas at 127 degrees Celsius. We have the concentrations for each of our gases here listed in the problem, and these are the answers for parts A, B, and C. Let's first work with A and look at it. So it says calculate the value of K at 127 degrees Celsius for this reaction. So to do that, we know we're going to get a value of K. So like before, we're going to say K equals the products raised to their power, so NH3 squared over N2 to the first power, because there's a 1 in front, and H2 cubed, because there's a 3 in front. We're going to plug in our proper concentrations here, and when we do this math, we're going to get the answer of 3.8 times 10 to the 4th. So that is for part A. Now for part B, so this blue part here is part B. We want to know 2 NH3, so here's the reaction. So we write the expression. These are our products, N2 and H2 cubed and NH3 squared. Plug in the values from the concentrations and we get that value. So when we do this, we're going to get 2.6 to negative fifth. Let's look at, compare them in a little bit quicker way. So as I look at A and B, do you notice, ask yourself the two famous questions we've asked ourselves several times throughout this year, forward or reverse. So what would I do to A to get it to look like B? Or, yes, so I would forward or reverse A, and what would I multiply by? So from A to B, I'd have to reverse it. So notice that B is the reverse of A. So if I reverse A, I have B. And then what would I need to multiply by? Well, to get to B, I have to multiply by 1. So if you notice, if we did the expression for A and the expression for B, expression for A here in black, the expression for B here in blue, they are the reciprocals of each other or the reverse of each other. I apologize, not reverse, inverse of each other. So that's kind of explained here. So here was our K for A, and this is our K for B. Above are the expressions for A and B. Do you notice that A to B are reciprocals or the inverse of each other? So if you recognize that you have a value of K for one kind of reaction, and all you would need to do is reverse it, then you can take the reciprocal of the value of K that you have. This is the button you're looking for on your calculator to understand how to do the reciprocal. So going to the next slide here, we know that A is the reciprocal of B, so that means I'd put 1 over Ka to get my B. So I would say then Ka is 3.8 times 10 to the 4th. We knew that from our calculations of plugging numbers into the black part. And then for B, I'm going to take 1 over what I got for Ka. Okay. This should actually be Kb. This is mistyped. Should be 1 over Ka. Okay. So that's what I did here. And that's how I got 2.6 to the negative fifth. Using that reciprocal button, you should see that button on your calculator. Okay, here we have example 3C in green. This is our work still from A. Now I'm doing my work from C. So here I have, just looking at the green right now, focusing here, I plugged in my, as I write an expression for this, I'd have NH3 concentration on top, N2 concentration on the bottom raised to the half power, and H2 concentration on the bottom raised to the 3/2 power. So then I plug in my concentrations that I'm given for this problem, and I apply the equilibrium constant work mathematically, and when I get this math, I will get 1.9 to the second. And let's see the shortcut for this. So ask yourself, from A to C, forward or reverse? It's forward because it's in the same order. What do I multiply by? To go from A to C, I multiplied by 1/2. Okay, so what we're going to do then is we are going to take the original K value and take it to the 1/2. So this is our original Ka expression, this is our Kc expression, and we are going to raise it to the 1/2 power. So to go, this again, this should be Kc. Got that backwards when I was thinking through this logically, so let me fix that with you all right now. We have Kc is going to be equal to Ka raised to the half power. Notice it's not under 1 because I didn't reverse it, so I should not put it under 1. All I did was multiply through by the factor of a half. So if we multiply through by a factor, we will raise K to that factor. So I multiplied through by a half, if you recall here. When I go through here, I multiply through by a half to go from A to C. So then I will take my Ka to the half power. So that's what I did here, and that's how I got that. 1.9 to the second. Now when raising it to the power, you can use your caret key to do that. So make sure that you can use your calculator and get this value for 3c. So what we did here is we basically generated some rules from example 3. We know that if we reverse a reaction, we can take the K of the forward reaction and put it under 1. So if I reverse it, it's 1 over K. If I raise something, multiply something, I raise it to a power. So if I multiply an expression by a factor of n, I raise K to that power of n to solve for the new value of K. So here are the rules that we just kind of talked about, and then some additional ones. Rules for using equilibrium constants. You have to have a balanced equation. If the coefficient isn't a balanced equation, it's multiply factor n, then the equilibrium constant is raised to that power. That's the last rule we just mentioned in 3c. This is 3c. The equilibrium constant for forward and reverse reactions are reciprocals of each other. This is what we did for 3b. We're going to talk about rule 4 here when we get to example 5. If a reaction can be expressed as the sum of 2 or more reactions, K for the overall reaction is the product. Now we did Hess's law, and we applied the same skill with Hess's law, but we added the values of delta H. Here we're going to multiply the values of K. A very important rule here, rule 5, liquids and solids are not part of your expression. So if you have something in a balanced equation that's in the liquid state or the solid state, you will not be putting it into your expression. Basically, it's a 1 and you leave it out of your expression, so you do not use it. Ions are in solution, or aqueous solutions will be part of your expressions. So no liquids or solids, only ions and gases. So AQs and gases should be in your expressions.